We want to discuss about the whole, average whole, and overall basic definitions for the mass flow diagram, and how to calculate the average whole. Of course, the borrow I have discussed about it. As you know, the whole in the mass whole diagram, normally we can even call it whole distance. This, of course, refers to the horizontal distance that the the earthwork must be transported from the point where it is excavated to the point where it is used or for embankment. I think you understand what I mean. So whole is you we can even sometimes call it whole distance. It refers to the horizontal distance or to the transportation distance that which is the horizontal distance that the earthwork has to be transported from the point where it is excavated, from the cut to the point where it is used for embankment or for fill. So the whole distance, it is the distance from the cut to the use. Of course, the whole distance normally is also known as the authorized hole. When you say hole, it is the authorized hole. It is between the origin and the final destination. So when you say origin and the final destination, that distance is known as the hole. Of course, the mass flow diagrams are used to calculate the average in the free hole between two given balance points. So we have the two balance points and also the average or free hole for the entire project area. This will depend, of course, on how the area is. So the average hole distance normally is equal to the area of the mass hole diagram, the area below the curve, that we divide by the total volume of materials moved. Total volume of materials moved. So the area of the mass hole diagram, it is the area between the mass hole curve and the balance line. Then the volume moved is the total volume of materials held between the balance points. The balance points. The balance points. Let us use the example. For example, here we have for this project, which is starting from 0 up to 600 meters. We want to compute, for example, the average hole distance. The average hole distance. So first of all, we have to define. First of all, we have to define the points. The points of balance. The points of balance. For example, for our project, let us say the points of balance, for example, are JK. And then the area between the mass hole curve and the balance line, because the balance line is this, and the area, what's the area? The area is this. The area is this. This is the area between the mass. So it's the area, of course, below. It's the area which is below the curve. It is here. So now, if you take this area, then you divide by the volume. What's the volume at this point? At this point, the volume is maybe 15,000. So it is this area which is scaled out. Then you divide it by the 15,000. Now, if we consider the points like the balance points are like here and there, from 0 up to 500. 0. So now we have the point, let us say P prime here. So now we be using now the whole total area, the whole total area. And now what will be the volume here? What's the volume here? The volume here is almost zero. This is zero, so we can't have. So for example, if you have this another balance line, like maybe the balance line like here, like EF, you can use this area and you have this volume of the 3000. But when you are here, the volume is zero. Sorry, not the volume, but yes, the volume is zero, and the area is too much. You see, like that way. So that's what we call the average hole distance. Then a longer hole distance means higher transportation cost. Of course, you require to use more fuel and the time, then and the more effort also. For example, a whole distance normally we say is the average distance, balance points. Usually, the whole distance is expressed in cubic meters, cubic meters, or station meters. You should, when you select the whole distance, you should also think of course, of the time and the fuel and the efforts which will be required. So balancing the cuts and the fields close together minimize the whole distance and thus reduces cost. So balancing cuts and fields which are very close to each other. For example, you can see the balance points like E and F is not the same as H and I, and is not the same as J and K. So you can see the shorter the balance cuts and fill, I mean the distance from here to here, the more the volumes are there also. You can see. So here, the maximum we have the volume which is zero. So maybe you can choose just in the middle here, like a JK, that is reasonable. And then you apply the area under the curve. For example, in this case, we have to scale out the area. So the area of course, below the curve, and then that one can be useful. Then there's also what you call overhaul. What does it mean by overhaul? Let's come back. So you can see how the calculation of average and the free hole. Two values you need to for the calculation: free hole area and the area and a volume. So now let's go to the next slide. Overhaul. What is the overhaul? Overhaul is the authorized hauling of excavation beyond the specified free hole. You know, we have a free hole, we have a hole, free hole, overhaul. The authorized hauling of excavation beyond the specified free hole is what we call the overhaul. So the free hole is the average hole for the project that has been, of course, accepted for use. And of course, overhaul is paid. Overhaul is paid for when you exceed when you exceed the average or free hole. This means that your average or free hole distance is exceeded within the balance points, so you do not have to pay for overhaul. Here we have a simple example I will share it with you, where we are required to draw the mass flow diagram. We have the changes from 0 to 1, 1 to 160, 16 to 2, 2 to that, and you have the volume here of cut, fill, cut. So you can see that from 0 up to 1, this is all cut, which is why the mass diagram continues to increase. Then from 1 up to 210. So if you try to draw this one, you have something which looks like this, which looks like this. If you try to draw, and then of course this shows you that this is a cut. The fill, you can see the fills are taking place. And then you can see at the end of the project, if this one goes up, we'll be having a waste. We're having a waste. Of course, these are some of the examples I am going to prepare and then share it with you. And what you have to know is that just wait. You can see on the whole mass flow diagram, always you have the changes and then you have the volumes. So you can see some distances, and then of course, when they're dealing with the earthwork excavation, the excavation, of course, will be treated as the material, the amount of materials that needs to be removed. That's what we have said from the grade. And this is the cuts. Then the embankment will be the amount of material that needs to be added to the grade. Excavation and embankments are calculated with the cross sections that we have seen previously. And what you have to also to take into account is that when you're dealing with the excavation, either there is what you call the topsoil, which are not calculated, and then there's imported soil, which is required, for example, to fulfill the quantity. Another point that I want to tell you is about that the behavior of the soil. Earthwork, here we are talking about the shrinkage. Let me insert a slide. Want to insert a slide and then explain something. So here we have to just wait. Shrinkage, bulking, shrinkage factor, bulking factor, or sometimes we call it swelling factor. So swelling factor I don't know whether shrinkage factor, I don't know whether there is another terminology, but shrinkage factor means that the soil that has been excavated and need to be used for embankment, we apply the shrinkage factor to the field, You understand? Because you may be required to fill like 100 cubic meters, but the materials that you are using, because it is shrinking, maybe by 10%. So now you need to have a volume of 110 cubic meters, so that if it shrinks, now it becomes 100% perfect. Then the bulking factor or the swelling factor, swelling factor. This one is the behavior of the materials which becomes less, and this is specifically applied to the excavation. This is applied to the excavation. You understand? This is applied to the excavation because excavate the materials many times may swell, may become too much, or may shrink. But in best practice, that's why you need to know the properties of the soil. Either it shrinks or either it swells. And the factors are supposed to be applied. So meaning that if you excavate, for example, 100 cubic meters, you may not need only to transport 100 cubic meters, but you need to transport maybe more, depending on the type of materials. This is a good example for you to go and look in the construction materials. Some of our materials, in engineering design, some materials, of course, are known to be swelling materials. Others are known to be shrinking material. Others are known for being bulking materials, and so on. So it is up to you to be good in of course, in geotechnical engineering, soil mechanics, so that we have the properties of the materials. So class, let me summarize what we have seen today for the mass hole diagram. The first point of the mass hole diagram is to understand what is a mass hole diagram. That's what is very important for you. Then, what is it used for? How do we draw a mass hole diagram? Then, what are the characteristics that the mass hole diagram can show us? And then, what could be the benefits of using a mass hole diagram? So please, maybe I have talked something. You need to go and read deeper. I can say I've got 76 students. You can go and read deeper and try to make sure that you have the basic understanding of a mass hole diagram, because a mass hole diagram is a very important tool as far as route surveying activities are concerned. So I will share with you maybe some notes later, but what I have talked today, I think it is enough. And this is the end of my today's class. I hope that the next class, of course, will be having a physical class because the graduation will be taking place tomorrow, and then I hope that by next week we'll be around. So please